All right, we are going to talk now about part B of classical field theory. I did another lecture on Lagrangian mechanics, and the big uh, conclusion of that lecture was deriving the Lagrangian density for our classical scalar field theory. Um, this part, we're going to basically take the Lagrangian density and convert it to Hamiltonian density, which will allow us to form the Hamiltonian for a classical field theory. And this will be the Hamiltonian for a quantum field theory, which we've talked about before. As you recall, we did a little bit of a divergence. Instead of continuing to talk about quantum field theory, we needed to finally talk about what our Hamiltonian is. And in order to figure out what that is, rather than just ad hoc give a statement, we use classical field theory, special relativity, arguments of symmetry, simplicity, locality to derive it. And the first part we derived the Lagrangian density using those principles. Now we'll show how to go from the Lagrangian density to the Hamiltonian density, which then gives us the Hamiltonian H. In order to do this, we have to use a very important theorem in modern physics, one of the most important theorems, and this was created by Noether, and it's called Noether's theorem. There's different forms of it, but I'm just going to call it Noether's theorem and focus on the main one for our purposes. I'll try to go slow and deliberate. There's a lot of high-level ideas here and a lot of notation, but I'll try to explain it as clearly as I can. Noether's theorem says that for every continuous symmetry transformation of the Lagrangian density L, there is a conserved quantity. Let phi of x be a scalar field. Remember, that's a real value number at every point in space. And again, we're taking off our quantum hats, just talking about classical physics, where everything just obtains a single real value at any given point in space for our scalar field phi. And associated with every scalar field phi, we can come up with our Lagrangian density, as we've showed in the previous lecture. So we have our points in space, x, y, z, and at every point in space, you can still think of it as a voxel, which has a ball moving up and down in space. In this case, a classical value where it just has a single value called phi of x. And we should have some sort of a formula or a postulate for our Lagrangian for this system. We came up with in a very explicit one using beautiful arguments of symmetry and locality in the previous lecture, but we basically have a Lagrangian that tells us if you give me the phi at this particular voxel, as well as the first derivatives of the phi, where you have to look at the next voxel in space and in time, called the mu phi. If you take those values at this voxel and put it into this Lagrangian formula, you will get another real number at that point called the Lagrangian density. That's our setup. And we talked about that in the previous lecture. Now, in order to understand Noether's theorem, imagine that we change phi of x at every single point in space and time. So we started with an initial field phi of x, and we suddenly apply a little deformation. We just go to every single point in space at every given time, and we change this phi of x to something a little bit different. And that new function you might want to call phi prime of x. And that phi prime of x is the old function, phi of x, plus this formula, some delta of phi of x, some small value that we're changing it. And this could be different at every point in space and time. So this delta phi of x itself is a function at every point in space and time, which gives you a real value, a small real value. And that's what modifies the original phi of x to give you a new scalar field phi prime of x. Of course, because we now have a new field phi prime of x, even if we use the same formula for the Lagrangian, which we assume we will now get a new value, a numerical value for the Lagrangian at every point in space, just because we changed phi. And when you change phi, you change that, which is an argument of the Lagrangian, and you'll also change, theoretically, the derivatives of phi. So that'll give you a new value for the Lagrangian at every point in space, which we could just call L prime. That's the old L of x plus this delta of the Lagrangian at every point in space. That happens automatically just from changing phi. Now, it's tempting to just say Noether's theorem says that if you have a symmetry transformation, you transform this phi of x to new phi of x, and the Lagrangian is totally unchanged. But Noether realized you don't actually have to be that restrictive. You don't have to say, we're only going to talk about symmetries where you change phi of x and the Lagrangian is entirely unchanged. Here's what Noether realized, and realized that this ends up resulting in a very important conserved quantity. We define instead the change in phi of x, delta phi of x, we call that a symmetry transformation if the change in the Lagrangian density is not zero, but something that can be expressed in this form. This is a four divergence form for those of you more familiar with special relativity, where we say d mu of f of mu equals the change in the Lagrangian with respect to x. For some particular set of functions fu, where you have a function f0, which is a scalar field, f1, which is a scalar field, f2, and f3 of x, all of which are scalar fields in space and time. And if you can express the change in Lagrangian that happens when you change the phi of x in this form as a four divergence of this function d mu, f mu, and of course the Einstein summation convention is implied here, then we call that this transformation of phi a symmetry transformation. Let me explain why that's so important, and that form really results in something very important. We start by recognizing that we can always derive another expression for del of the Lagrangian, of the change in the Lagrangian. The change in the Lagrangian is going to be equal to the rate at which the Lagrangian changes per change in unit phi multiplied by how much we're actually changing phi, so this part here, plus, remember this is a function, the Lagrangian, of not only phi, but of the derivatives of phi, which are called d mu phi, and there's four of them. So the range of change in Lagrangian with respect to how much you're changing these derivatives times delta of d mu of phi. So remember, the Lagrangian is a function of two variables. One is phi, and the other is d mu phi. Really have four more variables there, so five total. And we just want to see how much we're changing the d mu phi and how much we're changing the del phi, and multiplying that by the rate of change of the Lagrangian with respect to its argument will give us the total change in Lagrangian. A lot of symbols here, but the idea is inherently quite simple. Now, this formula here, delta of d mu of phi, can just be reversed. You can think about that for a few minutes and realize that it's very obvious as to why that's the case. So we can change this del and this, we can change this delta and this partial sub mu symbol and just kind of reverse them like this, and then rewrite this formula as follows. Delta of Lagrangian is equal to the partial derivative of the Lagrangian with respect to phi times delta phi plus the partial derivative of the Lagrangian with respect to d mu phi multiplied by, now just reversing this, d mu of the delta of phi. Now, this part of this change in Lagrangian can be rewritten as follows right over here using this line. And you can look at this for a couple of minutes. How did we get this line? Well, we just went back, if we go back here, just use the actual rule, the product rule of the derivative from basic calculus. If we take the derivative of a product of functions, that's equal to the derivative of the first term multiplied by the second term plus the derivative plus the first term multiplied by the derivative of the second term. If we just rearrange things here and solve for this term, and solve for this term over here, we get that is equal to this term minus this term. So that's how we got this formula here. If you notice this over here, that's identical to this. So we can re-express this using this equation, which is what I'm going to do now in the next line. We re-express this using this whole expression, and I did one more step where I pulled out the delta phi over here, and this is what I would get for my change in Lagrangian function. Change in Lagrangian is this minus this, and the whole thing in parentheses times delta phi plus this term over here. Now look at this term over here. This is the exact term, maybe multiplied by -1, that appears in our Euler-Lagrange equation. And remember, in the Euler-Lagrange equation, this term is equal to 0. The way I presented it in the previous lecture is -1 times this term. So this was plus and this was minus, but because it equals 0, I can flip the minus and plus sign, basically multiply it by -1. So assuming that my field, which we always assume is the law of physics, my classical field, that it obeys the principle of least action, we know that it gets its local marching order, so to speak, by the Euler-Lagrange equation, which is always going to be satisfied. So assuming that that is satisfied, this entire term is 0. So this gives us a simpler formula for the change in the Lagrangian as just this over here. Now, by assumption, our symmetry transformation that we performed caused a change in the Lagrangian like this. So now we have two different ways of expressing the change in Lagrangian. One, the assumption that our symmetry transformation, which was this change in phi, was of such a nature that the change in the Lagrangian can be expressed like this. But we know that the change in Lagrangian can always be expressed like this for any field obeying the Euler-Lagrange equation, which we assume is every field in physics. So these two terms have to be equal. And if we set them equal, this is what we get. If we swing this thing over to the other side and then pull out the partial derivative, this is the formula that we get. That d mu of this quantity over here is equal to 0. I'm just rewriting the same equation over here as we start this new slide. D mu of this quantity over here is equal to 0. Now, let's just call this entire quantity, which is somewhat complicated, it's fu, which, remember, fu is this kind of 4 sets of functions that we said are obeyed by our symmetry transformation. If we define this entire thing as fu minus this, which is also 4 different functions, depending on what mu you change here, you'll get one of 4 different functions. And if we define the whole thing as a large 4 vector, meaning we pick a mu here, like mu of 0, and then this would be 0, this would be 0, you get one number or one function there. If you change this to 1, you'll get the same thing, a different one, so on and so forth. But the whole constellation is a constellation of 4 functions, and we call that J mu. Then you can re-express this whole thing in this formula, which might be familiar for people that have taken some advanced courses in classical physics. That's d mu of J mu is equal to 0. And this formula itself is a conservation equation. Why? Because if you just expand it out using the Einstein summation convention, which we're using all along for repeated indices, we get that d0 j0 plus di ji is equal to 0. Or if you swing it over, we get that d0 j0 is equal to minus di ji, which this is the formula for the gradient of a vector field. Sorry, this is the formula for the divergence of a vector field minus the divergence of a vector field. So this is a conservation equation that occurs in physics, like, for example, in fluid mechanics, or when you're looking at conservation of charge and rate of current that's flowing. That's the exact form of our conservation equation. Just a brief review as to why that is. Well, the biggest thing is to realize that this part here, which is called the divergence or minus the divergence, represents how much of something is flowing out of a given area. So if you interpret this whole equation as saying that J0 is the density of something, how much stuff you have per unit volume, and if you interpret the other values of J, J1, J2, and J3 as how much of something is flowing, how much of something is flowing per unit area normal to the direction that it's flowing, which is J1, J2, and J3, then this whole thing becomes a conservation equation, as I'll show you now. So let's say you're talking about something, some sort of stuff that's flowing per unit normal area, and we call that J at a point X. Well, this diagram here shows that if this is the J of X over here, which means the rate at which this thing is flowing per unit normal area, and this is J of X plus dx, which is the value for this J vector over here, how much stuff is flowing per unit normal area, in this direction normal to the vector. Then if you just look at the x projection of this and the x projection of that, then you're going to get this, where j of x plus dx tells us how much of this stuff, whatever this is, represented by this spatial vector j, is flowing this way. This is the amount that's flowing out of it at x plus dx, minus j of x. This is the rate at which it's flowing into this here. And what we're seeing is that this difference over here tells us, at least if you only look at the x-axis, how much stuff is flowing out versus how much stuff is flowing in, which tells us the net amount that's flowing in the x-axis. You could do the same thing in the y-axis. I'm only showing a two-dimensional picture, but obviously you could do the same thing in the z-axis. So this entire quantity over here represents the rate of flow of stuff going inside of the box. If you multiply that by dx times dy, which is quote-unquote area of this box, or if you did it in 3 dimensions, dx, dy, dz, with the corresponding term here, that's the volume of this little box, then you get this formula over here. And this formula here, this part here, is exactly the divergence of this spatial vector field jx, jy. And you could expand this thing to 3 dimensions. As I mentioned, you get d to the third x, and the divergence of this vector field j in 3 dimensions. So this represents how much stuff is flowing out of here. If J0 is the density of stuff, which I'll get to in a second, and J itself is the flow of the stuff, the vector flow of that stuff per unit area normal to it. So basically this minus of the gradient represents the flow of this stuff, whatever you want to eventually talk about with stuff. It could be the flow of fluid, as I mentioned before, charge density, and how fast the current or the charge is flowing per unit area. But anyway, this minus of this represents the flow of stuff out of an infinitesimal box. So d0, j0 represents how fast stuff is leaving the infinitesimal box if j0 represents the spatial density of the stuff. So if you're talking about j0, if that somehow represents how much of this stuff you have per unit volume, the rate at which it's changing, d0, j0 represents how fast that stuff is leaving the infinitesimal blocks. So if that equals this, which also represents the rate at which stuff is flowing out of the infinitesimal box, then you have a true conservation, meaning that this thing j0, whatever is leaving it, is conserved. It goes somewhere else in space. Whatever is leaving it at one particular point in time is equal to the amount that it goes to the other points in space. So that's why this formula here, for those of you that are already familiar with classical physics at a reasonable level, you've probably seen this before, but that's why this formula is a conservation equation. Thus, d0, j0 equals minus the divergence of j is a conservation equation. It means that stuff is neither created nor destroyed, just moved from one region of space to another. And this conclusion here is that whatever this thing is, j0 ends up being important because it's the quote-unquote spatial density of the stuff that is conserved. It is the stuff that's conserved. So we were curious what this thing is here. That's actually what's being conserved. Remember, according to the divergence theorem, this is from multivariable calculus, local conservation equation d mu j mu equals 0 implies global conservation. Why? Let's say instead of talking about an infinitesimal box, we're talking about a large volume. This is just drawn in 2 dimensions, but imagine this is in a surface in 3 dimensions that's enclosed. Well, we know from the divergence theorem in multivariable calculus that that if you took the integral over d third x, the 3-dimensional integral of this, the divergence, which is a scalar field of this vector field j, and you integrate that over this inside area of this entire volume of this surface, which I give this name over here, lambda, you get the exact same value as if you just looked at the very surface or the very boundary of this thing and ignored the inside and just created a normal to every one of these points. multiplied by the vector value at the surface dotted with the normal vector to that surface over the 2D boundary. This is the divergence theorem, where you can look up any book on calculus, multivariable calculus, and see this being true. So what does that mean? Well, it means that let's think of Q as equal to something that's the integral of J0 throughout this entire area, throughout this entire 3D volume. So now we're integrating J0 throughout this entire volume. Well, then how fast is this thing Q, which is the total amount of it inside this volume, changing per unit time? Well, that really will, if assuming this is correct, that d mu j mu is equal to 0, that's going to be equal to the rate of flow of this stuff over the two-dimensional boundary. So, as we mentioned, if our entire field is confined, let's just say now that we have our entire field confined to a large but a finite region of space, meaning our field is this thing J that we're talking about here, J1, J2, and J3 really. And let's just say that it's only confined to some region of space, and our boundary here is infinitely large, so large that it gets past wherever our field exists. If that's the case, that this boundary is infinitely large and the value of the vector fields here are 0, then everything crossing here is 0, and there's nothing crossing here, and all the action happens inside this finite region of space. If that's the case, and we have this local conservation equation, then we have that dq dt is equal to 0, meaning this q, which is this total amount of stuff on the inside. J0 is the density of stuff at one given point in space, and we're integrating that density over all of our 3D volume. If our 3D volume is large enough to contain everything, it means that dq dt equals 0. So this q thing, as time goes on, will never change. The total amount of q will never change, assuming that we get this local conservation law. This is always true. If you have any kind of vector field that has this law, and you interpret things the way I said, then dq dt is equal to 0. Going back to Noether's theorem, we're going to apply what we said now to an infinitesimal space or time translation. Now, just to remind you, what we just showed with Noether's theorem is that if we have a symmetry transformation of our vector field, which means we go to every single point and we change it by some small amount, delta phi of x at every single point in space. If that causes a change in the Lagrangian, that's a symmetry transformation, meaning the Lagrangian not is unchanged, but can be expressed in that form, d mu f mu is equal to 0. Then we just showed with Noether's theorem, then there is a conserved quantity, this so-called J0. And we just showed with physical arguments why that equation, d mu j mu equals 0, implies a conserved quantity, but Noether's theorem itself says that d mu j mu ends up equals 0, ends up being the equation if you have a symmetry transformation. We're going to now apply this to probably the most important example, which is that we're going to apply the following very specific symmetry transformation. Suppose we change phi as follows. At any given space-time point, construct d mu phi as usual, where we have d mu phi is just this time derivative of phi and the spatial derivatives of phi. Now consider the 4 infinitesimal space-time vectors. Epsilon 0, and I put the 0 in parentheses, which itself is a 4 vector, which just this 4 vector of epsilon 0 is just a very small change in time, dx naught, and then 0 for everything else. And similarly with the I, j, and k components, that E1 is just a little change in the x-axis, E2 is a little change in the y-axis, and E3 is a little change in the z-axis. These are just four defined vectors, these four epsilons, 0, 1, 2, and 3. Let us individually look at four different cases / phi transformations. So now I'm going to use the same notation for everything, but just to be clear, we're only doing one, or at least we should think we're only just doing one transformation at a time, and we have four different ones. We can have the same notation and same derivations for all of them. But let's just say case eta. We change phi of x as follows. So the first type of thing we think we change phi of x as follows. We change phi of x to phi prime of x by doing the original phi of x plus some small change to it. Now, what is the small change? Well, here's how we do it. We take the derivative of phi d mu phi at any given spacetime point, and this actually represents a 4-vector, and we multiply that by our 4-vector epsilon. And depending on which of the four cases we want, we could make this eta 0 or 1 or 2 or 3, but we pick one of them. Let's just say we pick 0, for example. This would be 0 here. And this 0, this is a 4-vector here, 4-vector here. If we contract them, we get another scalar, and we're just changing our original phi by a scalar value at every point in space, at every given time. So this is an example of a transformation, of an infinitesimally small transformation, because this number is infinitesimally small. And this is just the derivative, which would be finite. So here's an example. So what is this? So we see that this is a transformation. And this is exactly what I'm saying. How much are we changing phi by? Delta phi is equal to epsilon mu d mu phi of x, just this part over here. And I'm going to go back for a second and just say, what does this transformation actually represent physically? It's worth pausing and thinking about that. We could just think mathematically, we're just changing it by this. But I want to show you what this particular transformation represents. Well, look at this over here. This, you have to follow along. This, it's not hard, but at the same time, you have to be a little careful with what we're thinking about and clear. If we start originally with an x-y axis, and we have a scalar field phi defined at any point xy. I'm just using a two-dimensional example. And we focus, for example, on this one point in space, A, and we want to know what phi at this point in space is. Well, we just plug in the spatial coordinates of this, which in this case I just say are 5, 4. So 5 hashes this way and 4 hashes this way. I plug that in, and I plug that into my function phi, and it spits out a number. And that number is phi at this particular spatial point 5 and 4. If I have my whole field here, I could also at this particular point in space not only define the value of phi, but I'll know the value of phi at the next adjacent point, so I could figure out its first derivatives, like d phi dx and d phi dy for spatial derivatives. Of course, I could do the same thing in time. Just for a moment, I'm just showing in a single moment in time, just for simplicity here. Now, let's just say our space is absolute here, and person, non-coordinate person who doesn't use primes on their, non-primed person who doesn't use primes on their axis, xy, has this axis to describe space. And now there's another person who's just still looking at the same field, but that person is the primed person who has axes x prime and y prime. And they're almost the same as xy, except they're just shifted over a tiny bit in the x-axis, nothing in the y-axis, a tiny bit dx in that axis. What happens when they try to look at this same spatial field? What happens to the formula that they come up with? And that's the question to ask. Now, the real question, you can ask different questions. So here they're separated by this amount dx. Let's say this primed person, what happens before that, talking about what they find, if they figure out the exact coordinates of this according to them, they'll get the same value because the field in space is unchanged. But what if they just put these two numbers, 5 and 4, into their coordinate system and see what happens? Well, if they do that in their coordinate system, in the prime coordinate system, then they also put out 5 hash points this way and 4 hash points that way, 5 this way and 4 that way. But when they do that, because their coordinate system is displaced, they're actually talking about a slightly different point in space. So when they put 5, 4 into their coordinate system, they're actually talking about this point in space versus the first guy who's not primed is talking about this point in space. So what is the relationship between these 2 points in space? Well, let's say the function that the prime guy gets is called, let's say that this thing here is called phi of a prime. Well, what is phi of a prime, which is this value right over here? Well, that's really equal to the value of phi at a plus the derivative of the function here times dx, because this thing is just separated an infinitesimal amount. So if you know the derivative of this, the rate at which it's changing here, multiplied by dx, that'll tell you its value at the next neighboring point, which is what we mean by phi of a prime. So what we can say in terms of functions is that if phi prime is the function that this prime guy will have to describe everything going on in space, that's equal to the phi function, which is what the non-prime guy will have, plus the derivative of phi with respect to x. This is of the non-prime guy at the point xy in the non-primed axis times dx. So that's all that this really means, is that if you look at this, we start with the function phi of x, and then we modify it in this very specific way by adding to it d phi dx, its derivative, times dx, and then we get this new function called phi prime xy. And what we showed physically, which is just somewhat interesting, is that that is exactly the form of the function that somebody would get if they just slide their axes over a little bit to the right, in this case, and look at the same exact function in the same exact space. So that's what that means physically when we do this kind of transformation. So going back to our slide, this was our transformation that we talked about. Phi prime of x is equal to phi of x plus this over here, which is the derivative of phi with respect to x, times this thing over here. And if you remember, this is our dx. And we have a different example for different cases. So in case 0, we're just straightly translating the time axis, meaning where do you start with your 0 time. In case 1, eta equals 1, we're saying that we're going right on the x-axis, just like our previous picture. Case 2 would be the y-axis. Case 3 would be the z-axis. All right, anyway, getting back to our math, we know what this now represents physically based on the previous argument. Delta phi of x is this part over here. This is our actual transformation. And one thing we know right away is that how should the Lagrangian change when we change our field from phi to phi prime of x by adding this small amount to everywhere? Well, it should actually change in exactly the same way. You can pause and think about that a little bit, but it should. That the Lagrangian itself, the new Lagrangian that you'll get at any given point once you change this, will be equal to the original Lagrangian plus this basic formula for how things change. The derivative of the Lagrangian at that point plus this little bit that you've changed to a different point. So think about this a little bit, but this should be exactly true, that the new Lagrangian L prime is equal to the original Lagrangian density, plus the rate at which Lagrangian was changing multiplied by how much you've translated in space. So this formula has to be true. You could think of it in terms of that coordinate system. That's a good way to get this answer here. So the change in the Lagrangian, whenever we do this type of transformation, is going to be this part over here, which is what this says. Delta of L is equal to epsilon mu d mu of L. And we can change the order of these two. Since this is constant, this is not changing. You're changing by you are changing by a fixed amount, epsilon mu. So dx0 is the same number at any given point in space. Dx1 is the same number at any point in space. Dx2 is the same number at any point in space. Dx3 is the same infinitesimal number at any given point in space. So you can just put this constant inside of here and get this expression over here. Well, what's so good about that? Well, here we go. So the change in the Lagrangian over here is equal to d mu of this thing over here. And if we just call this whole thing over here f mu, then we realize that we can express our whole Lagrangian in this quote-unquote standard form, that the change in Lagrangian that happens when you change phi in this way is exactly of this form, d mu f mu. This is a 4-gradient formula. And according to Noether and Noether's theorem, that's what we want. This type of transformation over here will result in a symmetry transformation. So this transformation of phi is a symmetry transformation. It satisfies this criteria that Noether said needs to happen. Once we know that we now are dealing with a symmetry transformation, which this proves, we know that there's a conserved quantity. And if I just listed some of the formulas from the derivation of Noether's theorem. Our conserved quantity, if you remember, is of this form, F mu minus this over here. And just rewriting some of the formula that we have over there, F mu, just based on the previous slide, was this thing over here. We have 4 different functions. The Lagrangian, which is a scalar field, but depending, again, there's 4 different cases of transformations here, but even if you pick one particular transformation, like in the x-axis, there's 4 particular values for mu. And if the x-axis, E0, for example, is 0, E1 is dx, E2 is, E superscript 2 is 0, and E3 is 0. But there's 4 functions here. And this, is, just to recall again, is our actual transformation that we're doing to the, that we're imposing on the scalar field. So if we just plug all this stuff in, this is what we get, that d mu of j mu is equal to 0. This is the formula that Noether promises us will be true if we define j mu as follows. F mu, which is this over here, minus this formula here, which I just rewrote here, times delta of phi, and delta of phi we have over here. So that's where this comes from. And just for notation, let's assume that in our 4 cases, whether we use dx0, dx1, dx2, and dx3, they're all of the same magnitude. And just so I don't have to write this whole thing down 4 times, I'm just going to assume that quantity is the absolute value of dx. You could just call it dx if you really wanted. Now, that means I can just kind of rewrite this epsilon function, which remember was, depending on what eta was, it was a small dx part to either 0, 1, 2, or 3. I can just rewrite that as a delta function here, like this, delta of mu sub eta times dx. This is the actual quantity. So if this is 0, if we're talking about eta is 0, we want the one where you're just transforming on the time axis. And then the only part of that, if you remember from E0, was non-zero, was the 0th component, and this will only give you 1. If that's correct, if this and this are both 0, and then we'll give you 0 otherwise. And then you multiply that by dx just to make sure it's infinitesimally small rather than the value of 1 as you get with the delta function. Now, I'm just going to rewrite this now using this little formula for epsilon. So d mu of, now instead of writing epsilon like this, I'm just going to write it delta of n mu. This is all the same delta. I'm just raising things here. Multiplied by dx L minus this derivative here. This here, I'm going to use this delta function again. And then keep this the same, is equal to 0. Now if I want, now I'm just going to divide both everything inside the parentheses here by minus this quantity dx, just to get rid of these dx's. I'm allowed to do that because this side is 0, so I can multiply this side by minus dx and this side by minus dx. And then because dx is constant with respect to space and time, I could pull that inside this derivative, and that'll cancel out these. And then the negative will kind of cause these two things to flip over. And it gives me this important formula, that d mu of this quantity here is equal to 0. We'll continue on the next slide. And this quantity over here is called the stress energy tensor over here. Just this entire quantity here is called the stress energy tensor. Now, we're not going to get into everything about the stress energy tensor, except for the very relevant part for us. But just to kind of look at this form, that remember, we have a different conservation, we have a separate conservation law for all the cases of eta. So if you just look at the coordinate case, if we transform on the x-axis, we have one conservation law. If we have transform on the y-axis, we get a different conservation law. Z-axis, different one. Time axis, different one. And that's represented by eta. Eta is either 0, 1, 2, or 3, depending on which one we're talking about. And then within that, you have some sort of a vector quantity, or like Ju that we're talking about in our conserved quantities, that itself has four quantities, a time component and 3 spatial components. So that's how you get this stress energy tensor. You give me which transformation you're talking about, which is eta, and I'll give you a 4 vector mu. The 0th component of which will become important. That's the stuff that's being conserved, which I'll show right now. Remember now, it's the 0th component of J mu of this whole thing that's conserved in a large enough region of space. And that's the quantity we really, really care about. We know that the J1, J2, and J3 represent something flowing, but if we have a very large region of space that we're talking about and all the stuff happens inside of it, nothing flows past that boundary, which we will eventually assume in quantum field theory that our experiments will just take place in the lab and not throughout the entire universe, which is how things work, then we can assume that there's something conserved throughout all of time as things are happening. And that is the 0th component of this big J vector. And what is that? Well, that's right over here. So this is the 0th component of that J vector right over here. For those familiar with some general relativity notation, this is kind of the formula for the stress energy tensor conservation, which may look familiar. But for our purposes, we don't have to get into the whole stress energy tensor part. We just care about the 0th component that is conserved. That means that at any given point in time, this value is going to be constant. The integral of this value over all of space that you're confining your experiment will be constant. It's this energy density. That's what this is over here. But it is the density. I'm using the word energy right off the bat. I'll get to that in a second. Now remember, we have 4 different cases. So this eta, depending on whether we're translating in the time direction or any of the spatial directions, this eta will be 0, 1, 2, or 3. So we get 4 different formulas, and you plug in the appropriate eta for what you're talking about. But the 0th component is conserved. Talked about that. If we just let eta equal to 0 and just talk about the time translation part and say that if we only just do an infinitesimal time transformation, we get a conserved quantity. That conserved quantity is called the Hamiltonian density, and its integral over all space is called the energy, or the Hamiltonian. That's what energy is. So when we have time translation symmetry, we realize there's a conserved quantity called the energy, or the total energy throughout all of space, which we also call the Hamiltonian. And that's the Hamiltonian that's going to be the big one that we're going to use. So here's the formula. The Hamiltonian is going to be the integral of this J0 when eta is 0, and that's what I plugged in here. Let's put eta equal to 0. We get a partial of L with respect to this is still 0, 0. And this part here is 0. And this part here is 0. And 0 of 0 is 1, which keeps of this delta function. And that's what gives us just L. So this whole thing here is the formula for the total Hamiltonian, which is conserved, meaning that it's totally unchanged throughout all of space. Energy is conserved. And this part here can just naturally be called the Hamiltonian density. So it's kind of the energy density at any given point in space. And this is the formula for it right here. Very important formula. Notice that if we have the Lagrangian, we now get the Hamiltonian, or if we have the Lagrangian density, we get the Hamiltonian density. And that was our goal. Remember in part 1, we used all these beautiful arguments to come up with the Lagrangian density, but we really wanted to get the Hamiltonian density. And this will give us the Hamiltonian, and this is the formula that we're using. That's how we get it. One other big thing I will say is that in classical mechanics of a particle, this quantity is very important, the partial derivative of the Lagrangian with respect to x dot. That is called the canonical momentum. And there are very simple, very good reasons you can look up in any classical field, in any classical mechanics book that talks about Lagrangian mechanics, even of just the particles. If you use this over here, you'll get the standard momentum that Newton used. And that extension of that idea, which is more powerful, gives you the canonical momentum. So this little part is called the canonical momentum, which means we can re-express this Hamiltonian density. Before we get to that, in a very similar fashion, in classical field theory, Lagrangian mechanics of classical field theory, we similarly define the canonical momentum as pi, and that's equal to very similar form here, the rate of change of Lagrangian with respect to how fast the field is changing, this over here. So that allows us to say, okay, this quantity here is this quantity here, and this gives us a very important way to go from Lagrangian to Hamiltonian that will come up over and over and over and over again in quantum field theory, but it comes from classical field theory arguments like we just showed. The Hamiltonian density is equal to pi, the canonical momentum, times phi dot minus the Lagrangian. You give me a Lagrangian, and I can use this formula to get to the Hamiltonian density, and I can go vice versa. In quantum field theory, we're over and over and over again going to start formulating the Lagrangian, and using this machine, we can get to our Hamiltonian density. And using the quantum field theory approach that we're going to use for our first part of our course, we need the Hamiltonian to keep moving forward. Getting a little on a tangent, but when we start doing part 2 of our course, we're going to do something called path integral, and we can just go right from Lagrangian to what we need to do, but we're not going to get ahead of ourselves. We want to build off of the quantum mechanics that we're familiar with from previous courses you may have taken, and that is mostly based on the Hamiltonian. What about the other components? Well, that's very important too, and it actually does come into play in a very nice way. So remember we said if we set eta equal to 0, we're talking about time translation symmetry, and we produced a conserved quantity called the energy, or Hamiltonian, and that came into play because that's what we're really looking for later on in quantum field theory, even though right now we're just doing classical field theory. But we just showed that we can change eta to 1, eta to 2, eta to 3 in each of those different cases, which respectively represent translation in the x, y, and z axis. Each of those cases gives us its own conserved quantity. And it turns out that gives a conserved quantity called the total momentum pi. It's different from pi when you have a classical field in the xi direction. So the total momentum of the entire field is also conserved, assuming again that you're talking about a large enough area that involves your whole experiment is taking place in some finite area, and you're thinking about the whole area around it. If you include that whole finite area, your total momentum is conserved, and here's the total momentum, pi, and that's the integral of this, of the j zeros with the different eta, eta of 1, eta 2 of eta 3, and you can just plug that in to the previous formula on the previous slide, or which is actually I just put over here. So if you set, for example, eta equal to 0, then if you set eta equal to I, which is the spatial translation, then you just get this part over here, and this part still stays unchanged. But if eta is equal to I, then this will always equal to 0, because 0 and 1, 2, or 3 of the delta function is going to equal 0. So this is the actual formula you get for the spatial density of momentum. And if you integrate that over all of space, you get the total momentum in the ith direction. Just saying what we said before, remember we call this quantity over here the canonical momentum of the field, is symbolized by pi in classical field theory, times this. You can also express this formula that way. So we now have some pretty big stuff here. We have used all of these arguments over the last 2 lectures to most importantly give us H. We're not totally done yet, but we now know that if you have a Lagrangian in this lecture, we can get to the Hamiltonian density. So the Lagrangian density gives us the Hamiltonian density. Integrate that to get the total Hamiltonian. We also similarly know that we can define a total momentum for a classical field as pi, and that's equal to this formula over here. And we know that the local definition for the canonical momentum is this over here. Now, let's just apply these ideas to the scalar field. That is our central example we've been talking about since lecture 1. We're just still right now going to talk about the scalar field, but not jump to quantum mechanics yet. So remember, using the first part A of our lecture, we derived using very beautiful arguments that this would be one of the simplest, if not the simplest, scalar field that nature might do. This would be the Lagrangian of the simplest scalar field right over here. And that will be our Lagrangian that we'll use and assume it actually is true for nature. And you can write that in this form over here. Now, what we thought would be more useful for us in the way we want to do quantum field theory is we needed a Hamiltonian. And now we're going to use everything we learned in this lecture, which is this. Basically, this summarizes the most important part of this lecture. We're going to use this to try to get our Hamiltonian density. And all we do is plug in the numbers. We know that pi, we mentioned before, is equal to this formula over here, dl d phi dot. And if you just look at this Lagrangian, especially in this form, the derivative of this with respect to phi dot is d0 phi, is just all this part. This will cancel, but there's no phi dot here, there's no phi dot here. This part does have a phi dot, and a phi dot is this whole thing here, so it's just like taking the derivative of x squared, for example, and then this will just become, this 2 will cancel this 1/2, and we'll just get phi dot. So this pi is equal to phi dot over here. That's this part over here. So these two things can be interchanged. Every time you see a phi dot, you can do pi, and anytime you see a pi, you can use a phi dot. And then that we just plug that into H for our Hamiltonian density. That's just equal to pi, and here's a phi dot, so I'm going to change that to pi, minus the Lagrangian, and that's just minus this whole thing over here, or this whole thing, whichever one you want to look at. That's minus 1/2 of phi dot, which I'm just going to change to pi again, squared, plus this minus becomes a plus 1/2 partial derivative with respect to I of phi, the whole quantity squared. This minus also becomes a plus this. This is pi squared minus 1/2 of pi squared, which was just total of plus 1/2 of pi squared. So that becomes positive 1/2 pi squared, which I can factor out. These are the 1/2 in each of these factors. And here's my final form for the Hamiltonian. This is the final result of those last 2 lectures, which is a lot of work. But this says we haven't even gotten to quantum mechanics. It says that, remember, we were trying to find a Hamiltonian for our system of voxels in quantum field theory. But in order to do that, we had to be inspired by a classical scalar field, which is the best representation of what we have. That's how you represent this ball going on a 1D track everywhere. So just only using classical field theory and using very compelling arguments of special relativity, which is symmetry in space and time, locality and simplicity, and basic results of Lagrangian mechanics, Noether's theorem, classical mechanics, and classical field theory. This is kind of our inevitable result. Pretty beautiful that this is the Hamiltonian density, and this is going to be our workhorse. I'll pause a little bit, but I'm going to give you a little flavor for what's next. This Hamiltonian density, as you can see, is expressed in terms of things that we know. Remember, we're not doing quantum mechanics yet, but we have a natural way of converting this expression. It couldn't be any more obvious if you looked at the first few lectures of how to convert this expression into one that makes sense on our Hilbert space. Remember, we have something called phi, which here is a real number, but there was a operator that tells us, that represents the position of the ball on the 1D track, same as the scalar field. We have pi, which is the canonical momentum here, and we had a very perfect expression for that that we used in our first couple of lectures on quantum field theory. And we've had an expression for this term over here, which we defined. All 3 of these terms are well defined on our Hilbert space, so it's very easy to extrapolate this to quantum field theory.